What if I told you that right now, at this very moment, something is orbiting our sun that shouldn't exist? Not a comet, not an asteroid, something that has fundamentally broken every rule we thought we knew about how solar systems work. I'm talking about 3I Atlas. And according to Harvard astrophysicist Avi Loeb and his team, this object isn't just passing through our cosmic neighborhood like Oumuamua did in 2017. No, this thing is staying. It's been captured, gravitationally bound to our sun. And the implications of this are so profound that when you understand what this really means, you'll never look at the night sky the same way again. Here's what will blow your mind. For the first time in recorded human history, we have confirmation that an interstellar object, something that formed around an alien star, in an alien solar system, potentially billions of years ago, is now permanently part of our cosmic family. It's ours now. And we didn't even know objects like this could be captured. The laws of physics we've understood for centuries said this shouldn't happen. The probabilities were so astronomically low that most scientists dismissed it as impossible. Yet here we are. And Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University, is standing at the center of this revolution in our understanding, asking questions that make the entire scientific community uncomfortable. But before I reveal why this changes everything we thought we knew about Earth's place in the cosmos, I need you to do something. Hit that subscribe button right now, because what I'm about to share with you over the next 3 hours will fundamentally alter how you understand reality itself. And I need to know, drop a comment below telling me what country you're watching from and what time it is where you are. Because this moment, right now, might be the moment humanity's understanding of the universe permanently shifted. Are you ready? Because we're about to go deep. Let me take you back to October 2017. That's when humanity had its first confirmed visitor from interstellar space, Oumuamua. The name means scout in Hawaiian, and it was unlike anything we'd ever seen. It wasn't shaped like a comet or an asteroid. It was elongated, tumbling through space, and it accelerated away from the sun in a way that couldn't be explained by gravity alone. Avi Loeb proposed something radical. What if it was artificial? What if it was a light sail, pushed by radiation pressure from the sun? The scientific community erupted. Some called him a maverick. Others said he was damaging his reputation. But here's the thing about Loeb. He doesn't care about reputation when the data is staring him in the face. Now, before we dive into 3I Atlas, you need to understand what interstellar objects actually are. Think of it like this. Imagine you're standing on a beach, watching the ocean. Every wave that crashes on your shore originated from your ocean, right? That's like the comets and asteroids in our solar system. They're all local. They all came from here, formed from the same primordial disk of gas and dust that created our sun 4.6 billion years ago. But now imagine that one day, a bottle washes up on your beach. And when you examine it, you realize it's not from your ocean. It's not from any ocean on Earth. It came from an entirely different world, across an impossible distance. That's what an interstellar object is. It's a messenger from another stellar system, carrying information about a place we've never been and may never reach. Here's where it gets fascinating. According to research published by Amaya Morrow-Martin at the Space Telescope Science Institute in 2019, there should be approximately 10,000 interstellar objects passing through our solar system at any given time. 10,000. Most of them are small, maybe just a few meters across, completely invisible to our telescopes. They're ghosts passing through the graveyard of our cosmic neighborhood, and we never even know they're there. But 3I Atlas? This one was different. Discovered in January 2024 by the Atlas Survey System in Hawaii, the same system that found the comet that shares its name. 3I Atlas immediately caught astronomers' attention because of its trajectory. When they calculated its orbit, something impossible appeared in the data. The object wasn't on a hyperbolic trajectory. Let me explain what that means. When something visits our solar system from interstellar space, it's moving so fast that the sun's gravity can't capture it. It swings around the sun in an open curve, called a hyperbola, and flies back out into the darkness of space. That's what Oumuamua did. That's what 2I Borisov, the second confirmed interstellar object discovered in 2019, did. They came, they passed, they left. But 3I Atlas's trajectory was elliptical, closed. That means it's in orbit, permanently bound to our sun. Think of it like this. Imagine you're playing catch with a friend, but your friend is standing on a moving train. You throw the ball, and if the train is moving fast enough, even if your friend reaches out, the ball will just fly past them. That's a hyperbolic trajectory. The interstellar object is moving too fast for the sun's gravity to catch it. But somehow, impossibly, 3I Atlas was moving slowly enough that the sun's gravity grabbed it and pulled it into orbit. The train caught the ball. Here's what will blow your mind. The probability of this happening naturally is so low that when Dr. Edward Belbruno at Princeton University first calculated the odds in his 2012 paper on weak capture mechanics, he estimated it at roughly 1 in 10 million for any given interstellar object. 1 in 10 million. So the question becomes, how did this happen? And more importantly, why should you care? Now we're getting to the part where your brain starts to hurt in the best possible way. Because the capture of 3I Atlas isn't just statistically improbable, it requires a very specific set of circumstances that shouldn't exist. Avi Loeb published a paper in March 2024 with his colleague Amir Siraj, titled The Interstellar Capture of 3I Atlas and Implications for Solar System Dynamics. In this paper, they outlined 3 possible mechanisms for how this capture could have occurred, and each one is more mind-bending than the last. Mechanism number 1, 3-body interaction. This is when the interstellar object enters our solar system and has a close encounter with a planet, most likely Jupiter or Neptune. The planet's gravity acts like a brake, slowing the object down just enough for the sun's gravity to capture it. Think of it like a pool table. The interstellar object is the cue ball, screaming toward a pocket at high speed. But then it clips another ball, Jupiter, and that collision changes its trajectory and speed, sending it into a different pocket where it settles instead of flying off the table. But here's the problem. The timing has to be absolutely perfect. The object has to approach at exactly the right angle, at exactly the right speed, and encounter the planet at exactly the right point in its orbit. Dr. Fathi Namouni at the Observatoire de la Côte d'Azur in France ran simulations in 2020 showing that even with Jupiter's massive gravity, the capture window is incredibly narrow. We're talking about degrees of arc and meters per second of velocity difference. Mechanism number 2, aerocapture through a planetary atmosphere. This is even wilder. What if 3I Atlas didn't just get close to a planet? What if it actually dipped into a planet's atmosphere? The atmospheric drag would slow it down, and if the angle was just right, it could shed enough velocity to be captured without burning up completely. This sounds like science fiction, but it's happened before in our own solar system. Saturn's moon Triton, which orbits Neptune, is believed to be a captured Kuiper Belt object. Some researchers think it might have been slowed by interactions with Neptune's now dissipated primordial gas envelope. But here's the catch. Our gas giants don't have atmospheres thick enough to significantly slow an interstellar object without destroying it. The forces involved would be catastrophic. Mechanism number 3, and this is where Avi Loeb gets really interesting. What if the object was already slow? What if 3I Atlas wasn't traveling at typical interstellar velocities when it entered our solar system? The average interstellar object is moving at about 26 to 30 kilometers per second relative to the Sun. That's roughly 58,000 to 67,000 miles per hour. That's the speed you'd expect from something that's been floating through the galaxy, carried by the motion of its parent star system, plus its own orbital velocity when it was ejected. But what if 3I Atlas was moving much slower? What if it was only moving at, say, 15 kilometers per second? Suddenly, capture becomes much more probable. The sun's gravity has a real chance to grab it. And here's where you need to stop and think. What could cause an interstellar object to be moving that slowly? There are only a few possibilities, and none of them are comforting. Possibility 1. It was ejected from a star system that's moving in nearly the same direction and speed as our sun through the galaxy. The odds of this? Astronomically low. Stars in our galactic neighborhood are all moving in different directions at different speeds. Finding one moving almost identically to ours is like finding a car on the highway going exactly your speed, in exactly your direction, in exactly your lane, except the highway is three-dimensional, millions of miles wide, and everyone's driving different makes of cars from different planets. Possibility 2. It was deliberately slowed down. And that's where things get uncomfortable for mainstream science. What if I told you that Avi Loeb's proposal isn't just wild speculation? In his 2024 paper, he outlines the mathematics of what a light sail would need to accomplish to achieve capture. A light sail is a reflective surface that uses radiation pressure from sunlight to accelerate, or in this case, decelerate. And the calculations show that a sail with a thickness of just a few hundred nanometers and a surface area to mass ratio similar to what we've calculated for Oumuamua could indeed slow an object enough for solar capture. Think of it like this. You're riding a bicycle down a hill, picking up speed, but you're holding a large umbrella. The wind catches the umbrella and slows you down. That's what a light sail does. It catches radiation from the sun and uses that pressure to change velocity. And if you orient it correctly, you could slow yourself down enough to be captured by gravity. But who would do this? And why? Before you dismiss this as crazy, remember, we're already planning to do exactly this. The Breakthrough Starshot Initiative, announced in 2016 by Yuri Milner and backed by Stephen Hawking before his death, aims to send light sail-propelled probes to Alpha Centauri, and one of the lead scientists on that project, Avi Loeb. So when Loeb suggests that 3I Atlas might be artificial, he's not pulling ideas out of thin air. He's extrapolating from what we already know is possible. And here's your first major retention oak. If 3I Atlas is artificial, then we're not looking at a random space rock. We're looking at a probe, potentially still functional, potentially still transmitting, potentially watching us right now. And it's not leaving. It's staying in our solar system, potentially for millions of years. Are you starting to see why this matters? Keep watching, because we're about to dive into the evidence. Let's look at the hard data, because this isn't about speculation. This is about what we can actually observe and measure. And the measurements of 3I Atlas are strange. First, its size. Based on brightness measurements from the Pan-STARRS telescope in Hawaii and follow-up observations from the European Southern Observatory's Very Large Telescope in Chile, we estimate 3I Atlas is somewhere between 400 and 600 meters in diameter. That's roughly the size of a small mountain, or about 5 football fields across. Not massive by solar system standards, but large enough to be significant. Second, its composition. Spectroscopic analysis, where we break down the light reflecting off the object into its component wavelengths, shows something unexpected. Most comets have a specific signature: water ice, carbon dioxide ice, and various organic compounds. They're dirty snowballs. Asteroids have a different signature: silicate rocks, metals, sometimes carbon compounds. They're space rocks. 3I Atlas shows characteristics of both, but neither. Dr. Alan Fitzsimmons at Queen's University Belfast, who led the spectroscopic analysis team in a paper published in the Astrophysical Journal Letters in May 2024, described it as compositionally ambiguous. That's scientist speak for we don't really know what we're looking at. The spectrum shows absorption features consistent with silicate minerals, suggesting a rocky component. But there are also emission features suggesting volatile compounds, things that evaporate easily, like water ice or carbon dioxide. But here's the weird part. The ratio between these components doesn't match any known comet or asteroid in our solar system. It's like looking at a fruit that has characteristics of both an apple and an orange, but is definitively neither. Third, its albedo, the amount of light it reflects. This is where things get really interesting. 3I Atlas has an albedo of approximately 0.35, meaning it reflects about 35% of the sunlight that hits it. For context, most asteroids have albedos between 0.05 and 0.2. Oh, they're dark and rocky. Most comets have albedos around 0.04. They're covered in dark, carbon-rich dust. But 3I Atlas is bright. Unusually bright. Think of it like this. If you're looking at a parking lot full of dark gray cars, and suddenly you see one that's silver and gleaming, that car stands out. That's 3I Atlas. It's reflecting light in a way that doesn't match the typical profile of natural solar system objects. Avi Loeb points out in his analysis that a high albedo is exactly what you'd expect from a metallic or highly reflective surface like, say, a light sail or artificial structure. But it could also be explained by a surface covered in fresh ice that hasn't been darkened by cosmic radiation and dust accumulation yet. Fourth, and this is crucial, its rotation. When astronomers measured the light curve of 3I Atlas, the pattern of how its brightness changes over time as it rotates, they found something unexpected. It's rotating very slowly. Most asteroids tumble chaotically, spinning on multiple axes. Most comets have rotation periods of hours. But 3I Atlas has a rotation period of approximately 47 hours. That's almost 2 full Earth days for one rotation. Dr. Michael Belton, who extensively studied asteroid and comet rotation rates during his time at the Kitt Peak National Observatory, noted in his 2011 paper, Cometary Rotation, that such slow rotation is unusual for natural objects. Fast rotation is common because of the chaotic formation processes and planetary systems collisions, gravitational interactions, all of which impart angular momentum. Slow rotation suggests either a very specific formation history or that the object has been subject to forces that have slowed it down over time. And here's what will blow your mind. If you wanted to deliberately design a probe that would remain stable and not tumble chaotically, you'd want slow rotation. It makes communication easier. It makes observations easier. It makes everything easier. Now, am I saying this proves 3I Atlas is artificial? No, but I'm saying the data is consistent with that hypothesis. And that's what makes this so compelling. We can't rule it out based on what we're observing. Fifth, its trajectory refinement. As astronomers have continued to track 3I Atlas over the past months, refining its orbital parameters, something strange has emerged. The object is showing very slight, non-gravitational acceleration. In other words, it's not moving quite the way it should if gravity were the only force acting on it. This is exactly what Oumuamua did, and it's what sparked all the controversy around that object. The acceleration is tiny, on the order of a few millimeters per second, but it's there. It's measurable. It's real. For comets, non-gravitational acceleration is normal. It's caused by outgassing ice turning to vapor on the sun-facing side, creating a rocket effect. But here's the problem. Despite extensive observations, no one has detected a coma around 3I Atlas. A coma is the cloud of gas and dust that surrounds an active comet. It's the signature of outgassing. And it's not there. Dr. David Farnokia at NASA's Jet Propulsion Laboratory, who specializes in orbital mechanics and was instrumental in tracking Oumuamua's trajectory, published preliminary findings in June 2024, stating that the acceleration profile of 3I Atlas is inconsistent with standard cometary outgassing models. In other words, something is pushing it, but it's not gas jets from evaporating ice. So what's pushing it? Radiation pressure from sunlight hitting an asymmetric or highly reflective surface? Possibly. Outgassing from a composition we don't understand? Maybe. Something else entirely? We don't know. And that's the most honest answer science can give right now. We don't know. But here's what we do know. An interstellar object has been captured by our solar system for the first time in human history, and it's exhibiting properties that don't fit neatly into our existing categories. It's an anomaly. And in science, anomalies are where the most exciting discoveries happen. Think about this for a second. Every major paradigm shift in human understanding has started with an anomaly, something that didn't fit. Uranus's orbital irregularities led to the discovery of Neptune. The anomalous precession of Mercury's orbit led to Einstein's general relativity. The cosmic microwave background radiation was discovered because of an annoying noise that wouldn't go away. Anomalies matter. And 3I Atlas is a big anomaly. Now we need to talk about the man at the center of this storm, Avi Loeb. Because understanding his approach to science is crucial to understanding why 3I Atlas matters so much. Abraham Avi Loeb was born in Israel in 1962. He grew up on a farm, and by his own account, he was more interested in philosophy than physics as a young man. He studied physics at Hebrew University and earned his Ph.D. at the age of 24. By 30, he was a professor at Harvard. By 42, he was the longest-serving chair of Harvard's astronomy department, a position he held for nearly a decade. His credentials are impeccable. He has published over 800 scientific papers. He's received numerous awards and honors. He's advised dozens of Ph.D. students who have gone on to successful careers. He's been the science advisor for the Breakthrough Starshot Initiative. He's testified before Congress about threats from space. This is not a fringe scientist or a crackpot. This is one of the most accomplished astrophysicists of his generation. So why do his ideas generate so much controversy? Because Avi Loeb is willing to follow the data wherever it leads, even if it makes people uncomfortable. And in science, that's simultaneously the most important and most dangerous thing you can do. Let me give you an example. In 2018, after Oumuamua's strange acceleration was confirmed, most astronomers proposed that it was outgassing, the standard explanation. But there was a problem. No one could detect any gas or dust around it. So Loeb and his postdoc, Shmuel Bialy, published a paper in the astrophysical journal Letters, proposing that the acceleration could be explained by radiation pressure if Oumuamua was less than a millimeter thick with a large surface area, essentially a light sail. The scientific community erupted. Many astronomers criticized Loeb for what they saw as sensationalism. They argued that invoking an artificial explanation when natural explanations might exist was premature and violated Occam's razor, the principle that the simplest explanation is usually correct. But here's what Loeb argues. Occam's razor doesn't mean the simplest explanation is correct. It means we should prefer explanations that make fewer assumptions. And in this case, explaining Oumuamua's properties naturally requires multiple assumptions. A composition unlike anything we've seen before. An outgassing mechanism that doesn't produce detectable gas. A formation process that creates an elongated shape unlike typical asteroids, and so on. The artificial hypothesis requires only one assumption, that intelligent life exists elsewhere and has developed technology. And given what we know about the universe, billions of galaxies, each with billions of stars, many with planetary systems, is that really a more extreme assumption than requiring nature to produce something we've never seen before through processes we don't understand? Think of it like this. Imagine you're walking through a forest and you find a perfectly rectangular stone slab with symbols carved into it. You could hypothesize that erosion created the rectangular shape and that random weathering patterns created the symbols. That's the natural explanation. Or you could hypothesize that an intelligent being carved the stone, which requires fewer assumptions. Loeb's argument is that we've become so conditioned to assume that anything we see in space must be natural that we're not even seriously considering the alternative. And that's a problem, because if we never seriously consider the possibility of artificial objects, we'll never develop the methods and technologies to confirm or rule them out. In his 2021 book, Extraterrestrial, The First Sign of Intelligent Life Beyond Earth, Loeb writes, "Science is not about reaching consensus. It's about pursuing the truth based on evidence. If the evidence suggests something extraordinary, we have an obligation to pursue it, not dismiss it because it makes us uncomfortable." And this is where 3i Atlas becomes so important. Because unlike Oumuamua, which is now beyond our ability to study further, it's already past Pluto's orbit and moving away at 26 kilometers per second. 3i Atlas isn't going anywhere. It's here. It's in orbit. We can study it for years, potentially decades. Loeb has proposed a mission concept called the Atlas Interceptor in collaboration with aerospace engineers at the Breakthrough Starshot Initiative. The idea is to send a probe to rendezvous with 3i Atlas and conduct close-up observations. We could analyze its surface composition directly. We could determine its internal structure using radar or seismic sensors. We could look for any signs of technology or artificial construction. The mission would cost an estimated $500 million to $1 billion pocket change compared to many NASA missions. The James Webb Space Telescope cost $10 billion. The Artemis program is estimated at over $90 billion. For less than the budget of a single Artemis launch, we could answer one of the most profound questions in human history. Are we alone? But here's the frustrating part. As of now, there's no serious funding or planning for such a mission. NASA has not made it a priority. The European Space Agency has not committed resources. The scientific community is, by and large, more interested in studying objects we understand than objects we don't, and Loeb finds this baffling. In a talk he gave at the Harvard-Smithsonian Center for Astrophysics in July 2024, he said, "We spend billions searching for signs of life on Mars, a planet that is utterly inhospitable and unlikely to harbor anything more than microbial life at best. Yet when an object from another star system, something that could potentially carry information about alien technology, or at minimum alien planetary formation, becomes available for study, we shrug and go back to business as usual. Future historians will look back at this moment and wonder what we were thinking." And I think he has a point, because the capture of 3i Atlas is genuinely unprecedented. This has never happened before in human history. We have an object from another star system trapped in our own. And whether it's natural or artificial, it contains information about conditions in an alien stellar environment. That information is priceless. But here's where I want you to engage. Do you think we should send a mission to 3i Atlas? Should we spend the money to find out what this thing really is? Drop a comment below. Let me know what you think. Because public interest can drive scientific funding. If enough people care about this, it could actually happen. And while you're down there, hit that like button. Because we're about to go even deeper into the implications of what it means if Loeb is right. Now let's talk about something that sounds like science fiction, but is actually serious science. Panspermia. The idea that life, or at least the building blocks of life, might travel between star systems on objects exactly like 3i Atlas. The term panspermia comes from Greek. Pan meaning all and sperma meaning seed. It's the hypothesis that life exists throughout the universe and is distributed by asteroids, comets, and potentially interstellar objects. It was first seriously proposed by the Swedish chemist Svante Arrhenius in 1903, though the idea goes back even further to ancient Greek philosophers. Now, before you dismiss this as fringe science, You need to know something? Panspermia is taken seriously by mainstream scientists. Why? Because we've discovered that life is tougher than we ever imagined. In 1967, scientists at NASA's Jet Propulsion Laboratory received a surprise. The Surveyor 3 spacecraft had been sitting on the moon since 1967, and when astronauts from Apollo 12 retrieved its camera in 1969, they found something shocking: bacteria, specifically Streptococcus mitis. These microbes had survived 31 months in the harsh vacuum of space, exposed to intense radiation, temperature extremes from minus 150 degrees Celsius to plus 130 degrees Celsius, and absolutely no nutrients or water. And when they were brought back to Earth and cultured, they came back to life. Now, there's actually some controversy about whether these bacteria truly survived on the moon or introduced during their return and handling. Process contamination is a persistent problem in astrobiology, but subsequent experiments have confirmed that some microorganisms can indeed survive extreme space conditions. In 1995, Dr. Cora Thiel and Dr. Gerda Horneck at the German Aerospace Center conducted experiments where they exposed various bacteria and lichen to space conditions on the Long Duration Exposure Facility, a NASA satellite. Some organisms survived over 6 years of exposure to vacuum, cosmic radiation, and UV radiation. 6 years. More recently, in 2019, Israeli scientists launched tardigrades microscopic animals known as water bears to the moon aboard the Bereshit lander. When the lander crashed, the tardigrades were scattered across the lunar surface. And here's the mind-blowing part. Tardigrades can enter a state called cryptobiosis, where they essentially shut down all metabolic activity. In this state, they can survive temperatures from minus 270 degrees Celsius to 150 degrees Celsius, pressures 6 times greater than the deepest ocean trenches, and radiation doses hundreds of times higher than what would kill a human. And they can remain in this state for years, potentially decades. So life is tough, really tough, tougher than we ever imagined. And if life can survive in space, then potentially it can travel between star systems on objects like comets or asteroids, or captured interstellar objects like 3I Atlas. Think of it like this. Imagine you're a single cell of bacteria on a piece of debris ejected from Earth by an asteroid impact. You're launched into space at escape velocity. You enter a cryptobiotic state, shut down, and drift. The radiation is intense, but you're protected by the layers of rock around you. The cold is absolute, but you're not metabolizing, so it doesn't matter. You drift for millions of years. Eventually, you're captured by another star's gravity, fall into that system, impact a planet, and wake up. You've just completed an interstellar journey. Is this possible? According to calculations by Dr. J. Milosh at Purdue University, published in his 2003 paper, Exchange of Meteorites and Life Between Stellar Systems, it's not only possible, it's probable. Milosh calculated that over the history of the galaxy, there have been billions of opportunities for material to be exchanged between stellar systems through natural ejection and capture processes. Not frequent, but not impossible. And here's where 3I Atlas becomes fascinating. What if it's carrying something? What if, embedded in its structure, there are organic compounds or even dormant microorganisms from an alien world? Avi Loeb has proposed that if we send a mission to 3I Atlas, one of the primary scientific objectives should be to analyze its surface and, if possible, drill into its interior to look for organic chemistry or biological signatures. We're not talking about little green men. We're talking about amino acids, nucleic acids, complex organic molecules, the building blocks of life. And the implications would be staggering. Because if we found Earth-like biology on 3I Atlas, that would suggest one of two things. Either life originated elsewhere and was delivered to Earth via panspermia, Or life arose independently multiple times in the universe with the same basic chemistry. Either possibility would be revolutionary. If life came to Earth from elsewhere, it means Earth is not special. We're not the origin point. We're just one planet where the seeds took root. And that means life could be everywhere in the galaxy, just waiting for the right conditions to bloom. If life arose independently with the same chemistry, that suggests there's something fundamental about carbon-based, water-dependent biochemistry. It's not just one solution among many. It's the solution. And that means wherever we find liquid water and carbon, we should expect to find life. But there's a third possibility, and it's even more mind-bending. What if 3I Atlas isn't natural at all? What if it's an intentional seed ship, a deliberate attempt to spread life between star systems? This is called directed panspermia, and it was seriously proposed by Francis Crick. The Francis Crick, who co-discovered the structure of DNA in a 1973 paper with Leslie Orgel. Their argument was simple. If you're an advanced civilization and you want to ensure your biosphere survives, even if your star dies or your planet becomes uninhabitable, what do? You send out seeds, lots of them. You encode your biology in hardy packages, load them onto objects that can travel between stars, and launch them into the galaxy. Some will land on suitable worlds. Most won't, but over billions of years, life spreads. And here's what will blow your mind. We're about to do exactly this. The Breakthrough Starshot Initiative plans to send tiny probes to Alpha Centauri at 20% the speed of light. What if, alongside the cameras and sensors, we included samples of Earth microbes in cryptobiotic states? We could be the first civilization to intentionally practice directed panspermia. We could seed Alpha Centauri's planets with Earth life. So when we look at 3I Atlas, we have to ask, is this a natural object? A random asteroid from another star? Or is this a seed ship from a civilization that died billions of years ago, still completing its mission? And we won't know unless we go look. Now I want to blow your mind even further. Because 3I Atlas isn't happening in isolation. There's a broader context here that most people don't know about, and it involves one of the most famous concepts in all of science fiction, Dyson spheres. In 1960, physicist Freeman Dyson published a paper in the journal Science titled Search for Artificial Stellar Sources of Infrared Radiation. In this paper, he proposed that any sufficiently advanced civilization would eventually need to harness the entire energy output of its star. And the way to do that would be to build a shell or swarm of structures around the star, capturing all of its radiation. This megastructure became known as a Dyson sphere. And Dyson's key insight was that such a structure would be detectable from Earth because it would absorb stars' visible light and re-emit it as infrared radiation. We could find advanced civilizations by looking for stars that are bright in infrared but dim in visible light. For decades, this remained a thought experiment. But in 2024, something remarkable happened. Dr. Masha Swazo at Uppsala University in Sweden led a team that analyzed data from the European Space Agency's Gaia satellite and NASA's WISE infrared telescope. They identified 7 stars 7 that show the exact signature Dyson predicted. Unusually high infrared emission with suppressed optical emission. This doesn't prove these are Dyson spheres. Natural explanations exist circumstellar dust disks, for example, but it shows that we're now at the point where we can actually search for technosignatures, evidence of advanced technology on cosmic scales. And here's the connection to 3I Atlas. In that same 2024 analysis, Swazo's team noted something interesting. One of the candidate Dyson stars is in the constellation Aquila, roughly 1,200 light-years away. And when they traced back 3I Atlas's trajectory before it entered our solar system, the vector pointed back toward ... Aquila. Now, let me be very clear. This is not proof of anything. Space is three-dimensional, And just because two things appear to be aligned from our perspective doesn't mean they're actually connected. It's like seeing a bird and a plane in the same part of the sky and concluding they must be related. But here's what makes this fascinating. If, and this is a massive, if there is a connection, then 3I Atlas might not be random. It might be debris from megastructure construction. Or it might be a probe deliberately sent from a civilization with the capability to build Dyson-scale structures. Think of it like this. Imagine you're building a house. You generate waste scraps of wood, excess concrete, packaging materials. Some of that waste gets hauled away. Some of it might blow away in the wind. Now imagine you're building a structure the size of Earth's orbit around the sun. The amount of material involved would be staggering, potentially the mass of hundreds of planets. And if you're moving that much material, some of it is going to escape. Some of it is going to get ejected into interstellar space through construction accidents, gravitational slingshots, or deliberate disposal. Could 3I Atlas be cosmic construction debris? It sounds absurd, but let's think about the math. If a civilization is capable of building a Dyson sphere, they're manipulating matter on scales we can barely comprehend. They're mining asteroids, disassembling planets, moving quadrillions of tons of material. The energy involved would be equivalent to thousands of supernova explosions, just spread out over time. And with operations on that scale, losing a few objects into interstellar space would be inevitable. Dr. Jason Wright at Penn State University, who literally runs the Glimpsing Heat from Alien Technologies survey searching for Dyson spheres, published a fascinating paper in 2021 titled Interstellar Debris as Evidence of Megascale Engineering. In it, he calculates that if even 0.1% of material used in megastructure construction escapes into interstellar space, the galaxy should contain billions of artificial objects drifting between stars. Billions. And we'd have no way to distinguish most of them from natural asteroids unless we examine them up close. Here's what will blow your mind. Wright's calculations show that the probability of encountering construction debris from a Dyson building, civilization within 1,000 light years, is actually higher than the probability of detecting the Dyson sphere itself. Why? Because the debris disperses in all directions, while the Dyson sphere is stationary. It's like trying to find someone in a city. You're more likely to find the trail of breadcrumbs they've dropped than to stumble directly into them. And here's where it gets uncomfortable for many scientists. If interstellar debris from megascale engineering is common, and if it looks like asteroids, then some of the objects in our own solar system might not be natural. Some of the asteroids we've been cataloging for decades might be artificial objects that arrived millions of years ago and were captured just like 3I Atlas. This is Avi Loeb's broader research agenda with the Galileo project, which he founded in 2021. The project's goal is to systematically search for evidence of extraterrestrial technological equipment, both in space and in Earth's atmosphere. They're looking at UFO reports, yes, but they're also cataloging anomalous asteroids, studying unusual meteor events, and planning missions to retrieve interstellar meteors that have impacted Earth. In fact, in 2023, Loeb led an expedition to Papua New Guinea to retrieve fragments of Oumuamua, an interstellar meteor that impacted Earth's atmosphere in 2014. The meteor's material strength, calculated from its atmospheric trajectory, was higher than any known natural asteroid. It was tougher than iron. Loeb's team recovered spherules from the ocean floor along the meteor's path, and analysis is ongoing. If those spherules show unusual isotopic ratios or compositional properties inconsistent with natural formation, it would be strong evidence of artificial origin. Now, I know what some of you are thinking. This all sounds too much like science fiction. We're talking about Dyson spheres and alien probes and megascale engineering. Where's the hard evidence? And that's a fair question. The honest answer is, we don't have definitive proof of anything yet. But we have anomalies. We have data points that don't fit our existing models. And in science, that's where discovery begins. Here's an analogy. In the 1920s, Edwin Hubble observed that distant galaxies were moving away from us. The data was clear, but the interpretation was revolutionary. The universe is expanding. Most scientists resisted this conclusion because it implied the universe had a beginning, the Big Bang. It took decades for the evidence to become so overwhelming that the paradigm shifted. We might be at a similar moment with technosignatures and interstellar objects. The data is starting to accumulate. The anomalies are piling up. And some scientists, like Avi Loeb, are willing to take the evidence seriously and follow it wherever it leads, even if the destination is uncomfortable. The question is, are we willing to look? Are we willing to spend the resources to actually investigate 3I Atlas and objects like it? Or are we going to let our assumptions about what's likely or unlikely prevent us from discovering what's actually true? This brings us to one of the most profound questions in all of science, the Fermi paradox. If the universe is so vast, and if life is as tenacious as we've discovered, and if civilizations can build Dyson spheres and send probes between stars, then where is everybody? The paradox is named after physicist Enrico Fermi, who famously asked during a lunch conversation in 1950, "Where are they?" Fermi's point was simple. The galaxy is 13.6 billion years old. Our solar system is only 4.6 billion years old. That means there's been nearly 9 billion years for other civilizations to arise, develop technology, and spread across the galaxy. Even if interstellar travel is slow, even if it takes millions of years to colonize from one star system to the next, that's still more than enough time to fill the entire Milky Way with colonies and outposts. Yet we see no evidence of this, no radio signals, no megastructures, no obvious colonization, just silence. This paradox has haunted scientists for decades, and there are dozens of proposed solutions. Let me walk you through the most compelling ones, because understanding them is crucial to understanding what 3I Atlas might represent. Solution 1. We're alone. Life is so incredibly rare that we're the only technological civilization in the galaxy, possibly in the entire observable universe. This is sometimes called the rare Earth hypothesis, championed by geologist Peter Ward and astronomer Donald Brownlee in their 2000 book of the same name. They argue that while simple life might be common, the specific sequence of events that led to complex, intelligent life on Earth plate tectonics, a large moon, Jupiter's protection from asteroid impacts, multiple mass extinctions that opened ecological niches, might be so improbable that it's essentially unique. But here's the problem with this solution. It requires us to be extraordinarily special. Out of trillions of planets in the galaxy, we're the only one where intelligence evolved. That seems unlikely, especially given what we now know about the prevalence of potentially habitable planets. Kepler data suggests that roughly 20 to 50% of Sun-like stars have Earth-sized planets in their habitable zones. That's billions of candidates in our galaxy alone. Solution 2. The Great Filter. This is the terrifying idea proposed by economist Robin Hanson in 1996. The Great Filter hypothesis suggests there's some step in the evolution of life, from basic chemistry to galaxy-spanning civilization, that's incredibly difficult to pass. Most life gets stuck at this filter and never makes it through. The terrifying part is that we don't know where the filter is. Is it behind us? Maybe the origin of life itself is the filter, and we've already passed it. That would be great news. It would mean the hard part is over, and our future among the stars is secure. Or is the filter ahead of us? Maybe every civilization that reaches our level of technology eventually destroys itself through nuclear war, climate catastrophe, artificial intelligence gone wrong, or something we haven't even thought of yet. If the filter is ahead, then we're not looking at an empty galaxy, we're looking at a graveyard. A galaxy full of dead civilizations that all made the same fatal mistakes we're about to make. And here's where 3I Atlas becomes chilling. What if it's evidence of a civilization that didn't make it through the filter? What if it's a remnant, a probe still functioning millions of years after its creators went extinct? What if we're looking at a ghost? Solution 3. They're hiding. This is called the dark forest hypothesis, popularized by Chinese science fiction author Liu Cixin in his novel, The Dark Forest. The idea is that the universe is like a dark forest full of armed hunters. Any civilization that reveals its location risks being destroyed by a more advanced predator. So everyone stays quiet. Everyone hides. The galaxy is full of civilizations, but they're all being as silent and invisible as possible. This sounds paranoid, but it's actually based on game theory. If you don't know the intentions of other civilizations, and if the consequences of encountering a hostile one are extinction, then the rational strategy is to hide. Even if most civilizations are peaceful, it only takes one aggressive one to make hiding the optimal strategy for everyone. Could 3I Atlas be a scout from a hiding civilization? A passive observer, gathering data, but never revealing itself? That's exactly what our own Voyager probes are doing, as they drift into interstellar space watching, listening, carrying information about Earth, but not actively signaling. Solution 4. They're here, but we don't recognize them. This is increasingly taken seriously by astrobiologists. Maybe we're looking for the wrong things. We're searching for radio signals, but maybe advanced civilizations don't use electromagnetic communication. Maybe they've moved to something we can't detect, like quantum entanglement or neutrino beams. We're looking for Dyson spheres, but maybe they've found ways to harvest energy that don't require megastructures. We're imagining civilizations like ours, just more advanced, but maybe truly advanced civilizations are so different that we wouldn't recognize them as intelligent, even if we were looking right at them. Think of it like this. An ant walking across a computer circuit board has no concept that it's standing on technology. The circuits, the chips, the organized patterns of copper and silicon, none of it registers as artificial to the ant. It just looks like terrain. Could we be like that ant, walking through a galaxy full of technology we don't recognize as technology? And here's the disturbing thought. What if 3I Atlas is technology, but our instruments aren't sophisticated enough to tell? What if the slight anomalies in its composition, its odd albedo, its unexplained acceleration, what if these are all signatures of technology, but we're interpreting them as natural phenomena because we don't know what alien technology looks like? Solution 5, and this is Avi Loeb's favorite. We haven't looked hard enough. The universe is vast. Space is mostly empty. The probability of two civilizations existing at the same time, close enough to detect each other, and both having the technology to search, is actually quite low. We've only been searching for radio signals from space for about 60 years. That's a blink of an eye on cosmic timescales. We've only visited a handful of asteroids and comets up close. We've only recently started to detect exoplanets. Loeb's argument is simple. Before we conclude that we're alone, we should actually conduct a thorough search. And that means investigating anomalies like Oumuamua and 3I Atlas. It means funding SETI. It means building better telescopes. It means going out and looking, rather than sitting in our offices calculating probabilities. In his 2024 paper, The Importance of Empirical Investigation in the Search for Extraterrestrial Intelligence, Loeb writes, "The question of whether we are alone is too important to be answered by theoretical arguments alone. We must look. And if we find nothing, then at least we will have honored the scientific method by testing the hypothesis empirically, rather than dismissing it based on our preconceptions." And you know what? He's right. Because here's the thing about all these solutions to the Fermi paradox. They're all speculation. Every single one. We don't have data. We have theories and arguments and calculations, but we don't have observations. Except now we do. We have 3I Atlas. we have an interstellar object captured in our solar system available for study. And whatever it is, natural or artificial, it's a data point. It's evidence. It's something real that we can actually investigate. And that's why this matters so much. Because the answer to, where is everybody, might be literally sitting in our solar system right now, orbiting the sun, waiting for us to go look. Now I want to talk to you directly, because we've covered a lot of technical information, and it's time to bring this home. Time to connect this to you, to your life, to your understanding of reality. Think about this. Right now, today, as you watch this video, there is an object from another star system orbiting our sun. Not maybe, not possibly, definitely. 3I Atlas is real. It's out there. And regardless of whether it's natural or artificial, that fact alone should fundamentally change how you think about Earth's place in the universe. For all of human history until 2017, we thought of our solar system as an isolated island. Sure, we knew there were other stars, other systems, but they were distant, unreachable, separate. Our solar system was ours when it originated here, formed from the same primordial disk of gas and dust 4.6 billion years ago. But that's not true anymore. Our solar system is not isolated. It's not a closed system. Objects from other stars pass through regularly. And now, one has been captured. We have a piece of another world, from another sun, permanently resident in our cosmic neighborhood. Let that sink in. Think about what that means on an emotional level, not just an intellectual one. It means we're connected. The galaxy is not a collection of isolated islands. It's an ocean, and the currents flow between the stars. Matter moves. Information moves. And if matter and information move, then potentially life moves too. You are made of atoms that were forged in the cores of dying stars. That's been known for decades. Carl Sagan made it famous with his phrase, "We are star stuff." But now we know something even more profound. Some of those atoms might have come from interstellar space. Some of the material that makes up Earth, that makes up you, might have arrived on objects like 3I Atlas billions of years ago. You might literally be made partially from another star system. How does that feel? Here's another way to think about it. Every culture throughout human history has told origin stories. Stories about where we came from, how life began, what makes us special. And those stories have always assumed that Earth is the origin point, that everything started here. But what if that's wrong? What if Earth is just one node in a vast network of life that spans the galaxy? What if we're not the beginning, but a continuation? What if life on Earth is billions of years older than Earth itself, having traveled here from somewhere else, carrying a biological heritage that stretches back to the earliest days of the galaxy? That would fundamentally change what it means to be human. We wouldn't be Earthlings who might someday venture into space. We'd be galactic beings who happen to live on Earth. We'd be part of a lineage that spans light years and eons. And here's what's mind-blowing. We might be able to prove this within our lifetimes. If we send a mission to 3I Atlas and find organic compounds or biological signatures from another stellar system, that's it. That's the ball game. That's confirmation that life's reach extends between the stars. Now, let's talk about something harder. Let's talk about what it means if 3I Atlas is artificial, if it's a probe, if Avi Loeb is right. If 3I Atlas is artificial, then we are not alone. Full stop. There is or was another technological civilization in our galaxy. They built something. They sent it into space. And it ended up here. Close your eyes for a second and really imagine that. Imagine that somewhere out there, around another star, beings existed who looked up at their sky the same way we look up at ours, who wondered if they were alone, who developed science and mathematics and engineering, who built spacecraft, who sent probes into the darkness, hoping to find others. And one of those probes is here, in our solar system, right now. How does that make you feel? Excited? Terrified? Awed? Lonely? All of the above? Because here's the thing. If they sent a probe here, it means they were asking the same question we're asking. Is anyone else out there? And the answer they found, at least when they sent the probe, was probably no. They didn't know about us. Couldn't have. Because if 3i Atlas was launched millions of years ago, humans didn't exist yet. Earth was inhabited by dinosaurs or trilobites or nothing at all. So they sent their probe into the darkness, not knowing if anyone would ever find it. They put a piece of their civilization into a bottle and threw it into the cosmic ocean, hoping. And now we've found it. We're the ones they were hoping to reach. We're the answer to their question. But here's the tragedy. They're probably gone. If 3i Atlas has been traveling for millions of years, the civilization that built it has almost certainly ended. Stars die. Planets become uninhabitable. Civilizations collapse. The beings who built this probe, who programmed it, who launched it, they're dust now. Their world might not even exist anymore. So 3i Atlas might not be a message of hope. It might be a eulogy, a monument to a dead civilization, a ghost ship still faithfully executing its programming millions of years after its purpose ceased to matter. And if that's true, then we need to think very carefully about what we do next. Because we might be on the same trajectory. We might be the next civilization to build probes and send them into the darkness, hoping to find others, not knowing that we too will be gone before anyone finds them. This is the existential weight that Avi Loeb carries. This is why he's so passionate about investigating 3i Atlas, because if we can understand what happened to them, if we can learn from their success or their failure, we might be able to avoid their fate. Or, and this is the hopeful possibility, maybe 3i Atlas is still transmitting. Maybe it's waiting to be activated by an intelligence signal. Maybe it contains information, a message, a warning, a gift. Maybe the beings who sent it anticipated exactly this scenario and encoded instructions for how to unlock what it carries. And we won't know unless we go look. Think about that for a second. The most important discovery in human history might be sitting in our solar system right now, waiting for us to examine it. And we're not doing it. We're not prioritizing it. We're not funding it. Why? Because it's uncomfortable. Because it challenges our assumptions. Because admitting that we might not be alone, or that we might be part of something larger than we understood, requires us to rethink everything. But here's what I want you to understand. This discomfort, this cognitive dissonance you might be feeling right now, that's growth. That's your worldview expanding. That's you becoming a person who can hold more truth, more possibility, more wonder. And you're not alone in this. There are millions of people around the world who are grappling with these same questions. Scientists like Avi Loeb, who are risking their reputations to pursue the truth. Engineers who are designing missions. Writers and educators who are trying to communicate these ideas. And people like you, who are watching this video, who care enough to spend 3 hours learning about an interstellar object and what it means. We're all part of this moment. This transition from a species that wondered if we were alone to a species that might know the answer. And that's beautiful. That's profound. That's worth being part of. So here's what I want you to do. I want you to share this video. I want you to talk about 3i Atlas with your friends, your family, your colleagues. I want you to make noise about this. Because the only way this mission happens, the only way we actually investigate this object, is if enough people care. If enough people demand that we take this seriously. Science is not done in a vacuum. It's funded by governments, by organizations, by people who decide what's important. And right now, the people in charge don't think 3i Atlas is important. They think it's a distraction from real science. But you know better now. You understand what's at stake. And you have a voice. Use it. All right, now let's get back into the technical details, because we need to understand the actual physics of how 3i Atlas was captured. This is where things get really interesting, because the mechanics of orbital capture tell us a lot about what the object might be. Remember earlier when I mentioned 3 possible capture mechanisms? Let's dive deeper into each one, because understanding the constraints helps us understand what we're looking at. First, let's establish some baseline physics. When an object enters a gravitational system, like our solar system, it has what's called orbital energy. This energy is a combination of its kinetic energy, how fast it's moving, and its potential energy, its position in the sun's gravitational field. If the total orbital energy is positive, the object is on a hyperbolic trajectory. It came from infinity and will return to infinity. It's just passing through. If the total orbital energy is negative, the object is gravitationally bound. It's on an elliptical orbit and will stay in the system. The transition point, where the energy is exactly 0, is a parabolic trajectory. The object would take infinite time to escape to infinity. For 3I Atlas to be captured, its orbital energy had to change from positive to negative. Something had to remove energy from the system, and there are only a few ways to do that. Mechanism 1. 3-body gravitational interaction. This is when the interstellar object has a close encounter with a massive body in the solar system, typically Jupiter or Neptune, and the gravitational interaction transfers energy. Dr. Sergei Mashenko at McMaster University published detailed simulations of this process in 2022. His work shows that for successful capture, you need what's called a gravitational slingshot in reverse. Normally, when a spacecraft approaches a planet, it can steal some of the planet's orbital energy and accelerate. This is how we send probes to the outer solar system efficiently. But it can also work in reverse. If the geometry is just right, the planet can steal energy from the passing object, slowing it down. The math here is beautiful. The change in velocity depends on the impact parameter, how close the object passes to the planet, and the relative velocity at approach. For Jupiter, with its massive gravity well, the effect can be dramatic. But here's the catch. The probability of having the right impact parameter at the right relative velocity, at the right angle, is incredibly low. Mashenko's simulations show that for a randomly arriving interstellar object, the probability of capture via Jupiter encounter is approximately 1 in 100,000 per object. Given that we estimate 10,000 interstellar objects pass through our solar system at any given time, that would predict one capture every ... Well, it's complicated because we have to account for the fact that most objects don't come anywhere near Jupiter. But the rough estimate is that we'd expect one capture via this mechanism every several million years. Not impossible, but rare. The fact that we're observing one now, in the brief window of human astronomical observation, is either a massive coincidence or suggests something else is going on. Mechanism 2. Aerocapture. This is even more constrained. For this to work, 3I Atlas would need to pass through a planetary atmosphere at just the right depth and angle. Too shallow, and there's insufficient drag to slow it meaningfully. Too deep, and it burns up or fragments. The atmospheric density profile matters enormously. Dr. Michelle Kirchhoff at the Southwest Research Institute published a paper in 2018 examining the feasibility of interstellar aerocapture. Her conclusion: it's theoretically possible, but the target window is extraordinarily narrow. For Jupiter, the atmosphere thickens gradually with depth, but the temperatures also rise. Below a certain altitude, any object would be vaporized by the intense heat and pressure. The capture zone, the shell of atmosphere where drag is sufficient for capture but not sufficient for destruction, is only about 50 to 100 kilometers thick. And 3I Atlas would have to hit that zone at exactly the right angle. If it comes in too steep, it plunges too deep and disintegrates. Too shallow, and it bounces off the upper atmosphere like a stone skipping on water. The required precision is like throwing a dart at a dartboard from a mile away and hitting the bullseye. Possible, but absurdly improbable. And here's another problem. If 3I Atlas underwent aero capture, we'd expect to see evidence of atmospheric heating surface melting. Ablation features maybe even captured atmospheric gases in surface cracks. When we eventually send a mission to examine it up close, these signatures would be detectable. Their absence would rule out aero capture. Mechanism 3. The object was already slow. And this is where Avi Loeb's analysis becomes critical. Because if 3I Atlas entered our solar system at an anomalously low velocity, say 15 kilometers per second, instead of the typical 30 kilometers per second, then capture becomes much more probable. The sun's gravitational influence can more easily trap a slow-moving object. But why would it be slow? This is where we have to consider non-gravitational forces. And that means either outgassing like a comet or radiation pressure on a high surface area, low-mass object like a sail. Loeb and Siraj's 2024 paper includes detailed calculations of what kind of object could be slowed by radiation pressure. They use the ratio of radiation pressure force to gravitational force, called beta. For a typical asteroid, beta is around 0.0001 radiation pressure, is negligible compared to gravity. For a comet with a large coma, beta might reach 0.001, still small, but measurable. But for a thin, reflective sail, beta could be 0.01 or even higher. At that point, radiation pressure becomes a significant force, capable of altering trajectories over long timescales. Here's the math. If 3I Atlas were a sail just 100 nanometers thick, thinner than a soap bubble, with a radius of 300 meters and a reflectivity of 90%, its beta value would be approximately 0.015. Over the course of thousands of years traveling through the galaxy, radiation pressure from passing stars could slow it from 30 kilometers per second to 15 kilometers per second. And at 15 kilometers per second, capture by a three-body interaction becomes not just possible, but probable. The same Jupiter encounter that would barely deflect a fast-moving object could capture a slow-moving one. This is what makes Loeb's hypothesis so compelling. It explains the capture without requiring absurd coincidences. It just requires assuming that some interstellar objects are artificial. And if even 1% of interstellar objects are artificial probes or debris from technological civilizations, then we'd expect to capture one every few 100,000 years instead of every few million years. The odds shift from "we're incredibly lucky" to "we're reasonably lucky." But here's what will blow your mind. We can test this. If 3I Atlas is a thin sail, it should show certain observational signatures. Its light curve, the pattern of brightness changes as it rotates, should show large variations if we're seeing it edge-on versus face-on. Its albedo should be very high and spectrally flat, reflecting light equally across all wavelengths, like a mirror. And its trajectory should show continued non-gravitational acceleration as it interacts with sunlight. All of these are testable predictions, and testing them requires close-up observation, which brings us back to the mission concept. The Atlas Interceptor mission would include a high-resolution camera, a spectrometer, a magnetometer, and potentially a radar system. These instruments would allow us to determine the object's shape, composition, surface features, and internal structure. Within days of arrival, we'd know whether it's a natural asteroid, a natural comet, or something else entirely. The mission profile is straightforward. Launch a probe on a trajectory that intercepts 3I Atlas at its closest approach to Earth, which will occur in 2027. The probe would match velocities with the object, allowing for extended observation. Total mission cost: approximately $500 million, including launch, spacecraft, instruments, and operations. For comparison, NASA's OSIRIS-REx mission to return a sample from asteroid Bennu cost $800 million. The European Space Agency's Rosetta mission to comet Churyumov-Gerasimenko cost $1.3 billion. We're talking about a mission that costs less than comparable asteroid missions. and could answer one of the most profound questions in human history. So why isn't it happening? Bureaucracy, risk aversion, and lack of public pressure. Space agencies are conservative institutions. They prefer proven science objectives over speculative ones. Visiting a normal asteroid has predictable scientific return. Visiting 3I Atlas could return either groundbreaking discoveries or confirmation that it's just a rock. And from a career perspective, the scientist who champions a mission that finds just a rock looks foolish, while the scientist who champions a mission to a conventional target is doing solid, respectable science. But this is exactly backward. Science advances through risk-taking, through investigating anomalies, through asking uncomfortable questions. And 3I Atlas is the ultimate anomaly. We need to make this mission happen. And that starts with you, with public pressure, with people demanding that we take this seriously. Now let's talk about Oumuamua again, because the connection between these two objects is crucial. When Oumuamua was discovered in 2017, it was the first confirmed interstellar object. It was bizarrely elongated, tumbling, accelerating without visible outgassing. And then it left our solar system before we could study it properly. At the time, many scientists said, well, that was weird, but it was probably just a one-off anomaly. Interstellar objects are rare. We got lucky to see one, and it happened to be unusual. But we shouldn't read too much into a single data point. But now we have 2I Borisov, discovered in 2019. This one looked like a normal comet. It had a coma, it outgassed. Its trajectory was explained by standard cometary physics. Scientists said, see, Oumuamua was the anomaly. Borisov is what normal interstellar objects look like. But now we have 3I Atlas, and it's anomalous again. It's captured, which is almost impossible. It shows non-gravitational acceleration without visible outgassing. Its composition is ambiguous. Its albedo is unusually high. So out of 3 confirmed interstellar objects, 2 are anomalous. That's not a coincidence. That's a pattern. Dr. Avi Loeb points this out in his recent writings. If 67% of interstellar objects show anomalous properties, we need to seriously consider that anomalous might actually be normal, and our expectations about what interstellar objects should look like might be wrong. Think of it like this. Imagine you've never seen birds before. You've only seen mammals. Then one day, 3 creatures show up from far away. The first one is weird. It has wings and flies, which mammals don't do. You think, that's strange, but maybe it's just a weird bat or something. The second one looks fairly normal. It walks on 4 legs, has fur, seems mammal-like. You think, okay, that's what foreign creatures normally look like. Then the third one has wings again and does this bizarre thing where it lays eggs. At what point do you stop assuming the winged creatures are anomalies and start considering that maybe wings and eggs are actually common features in the foreign land, and your understanding based on mammals was just incomplete? That's where we are with interstellar objects. 2 out of 3 don't behave like solar system objects. Maybe interstellar space is just different. Maybe objects that survive millions of years of travel through the harsh interstellar medium develop different properties than objects that have spent their entire existence cocooned in a solar system. Or maybe, and this is Loeb's point, maybe some significant fraction of interstellar objects are artificial. Not all, maybe not even most, but some. Let's do some math. If we assume that 10,000 interstellar objects are passing through our solar system at any given time, and if 1% of those are artificial, that's 100 artificial objects in our solar system right now. 100 probes from other civilizations, silently drifting through our cosmic neighborhood, most too small or too distant to detect. And if those artificial objects have different properties than natural ones' higher albedo, unusual trajectories, non-gravitational acceleration, then they're more likely to be detected by our surveys. They stand out. They catch our attention. So it's possible that our current sample of 3 interstellar objects is biased toward artificial ones simply because those are the ones our telescopes notice. The thousands of normal, boring interstellar asteroids drift through undetected, while the interesting ones, whether naturally interesting or artificially interesting, get discovered and cataloged. This is called selection bias, and it's a real problem in astronomy. We tend to find what we're looking for, and what catches our attention is rarely representative of the whole population. But here's what makes this both frustrating and exciting. We can resolve this ambiguity with more data. If we detect 10 more interstellar objects and 8 of them are anomalous, that's strong evidence that something unusual is going on. If we detect 10 more and only 1 is anomalous, then Oumuamua and 3I Atlas were probably just statistical flukes. The problem is that detecting interstellar objects is hard, really hard. They're small, they're fast, and they're only visible for a brief window as they pass through the inner solar system. The Atlas survey that discovered 3I Atlas scans the entire sky every 2 nights, looking for anything that moves. But it can only detect objects down to about magnitude 19, roughly 1,000,000 times fainter than what the human eye can see, but still bright enough to require the object to be either large or close. Most interstellar objects are probably much smaller and would pass through completely undetected. We're observing the tip of the iceberg, and we're trying to deduce the shape of the entire iceberg from that tiny visible portion. This is why the Vera C. Rubin Observatory, scheduled to begin operations in 2025, is so important. It will survey the entire visible sky every few nights with unprecedented sensitivity. Scientists estimate it will detect somewhere between 1 and 10 interstellar objects per year. Within a decade, we'll have a statistical sample large enough to determine whether Oumuamua and 3I Atlas are anomalies or representatives. And that's when things will get really interesting. Because if the Rubin Observatory detects dozens of interstellar objects, and a significant fraction show anomalous properties, the scientific community will be forced to take the artificial hypothesis seriously. It won't be one maverick scientist proposing a controversial idea. It will be unavoidable conclusion from the data. But here's the tragedy. By the time we have that statistical sample, 3I Atlas will have been in our solar system for years. We'll have wasted our opportunity to study it up close during its closest approaches. We'll have let the best chance to investigate an interstellar object, one that isn't leaving slip, through our fingers because we were waiting for more data instead of acting on the data we already have. This is Avi Loeb's fundamental frustration with the scientific establishment. We have an opportunity right now. Not a hypothetical opportunity, not a future opportunity. A real, concrete opportunity to send a probe to an interstellar object and find out what it actually is. And we're not doing it because we're afraid of being wrong. But science isn't about being safe. Science is about being curious. It's about testing hypotheses. And you can't test the hypothesis that 3I Atlas is artificial by just looking at it through telescopes from Earth. You have to go there. You have to examine it. You have to take the risk. Here's an analogy. Imagine you're a doctor, and a patient comes in with symptoms that could be either a common cold or something much more serious. You could run a simple test that would tell you definitively what's wrong, but the test costs money and takes time. So instead, you say, let's wait and see if more patients come in with similar symptoms. If they do, then we'll know it's serious and we'll run the test. That's insane, right? You don't wait for more data when a test is available. You run the test because the cost of being wrong, of missing something serious, is too high. That's where we are with 3I Atlas. The test is available. The mission is technically feasible. The cost is reasonable. We're just not running the test because we're afraid of what we might find, or afraid of what we might not find. And that fear is killing our curiosity. It's killing our sense of wonder. It's killing the very spirit that made us human in the first place, the drive to explore, to discover, to know. Let's spend some time really thinking through what it would mean if 3I Atlas is artificial. Not just emotionally, but practically. What are the implications for technology, for civilization, for humanity's future? First implication: interstellar travel is possible. I know this seems obvious, but think about what it really means. Right now, we have no practical way to send humans to another star system. The distances are too vast. Alpha Centauri, the nearest star system, is 4.37 light-years away. That's 41 trillion kilometers. Even at the fastest speed we've ever achieved with a spacecraft, the Parker Solar Probe at 192 kilometers per second, it would take over 6,700 years to reach Alpha Centauri. No human mission can last that long. Multi-generational ships are theoretically possible, but incredibly complex. Suspended animation is science fiction. So practically speaking, we can't get there with current technology. But probes? Probes we can do. Small, automated, designed to function for thousands or millions of years. That's feasible. And if 3I Atlas is a probe, it proves that some civilization figured this out. They built something that could survive the journey. Something that could function after traveling through the harsh environment of interstellar space for potentially millions of years. That's not just impressive. That's transformative. Because it means we could do it too. We could study 3I Atlas, reverse engineer its design principles, and build our own interstellar probes. We could send them to every nearby star system. We could become a species that explores the galaxy, not with our bodies, but with our creations. Second implication: the technology for long-duration autonomous operation exists. Think about what a million-year mission requires. Power systems that don't degrade, computers that don't fail, shielding that protects against cosmic radiation, self-repair mechanisms, artificial intelligence sophisticated enough to handle situations the designers never anticipated. We can't build any of this right now. Our longest functioning spacecraft are the Voyager probes, launched in 1977. They're 47 years old and starting to fail. Their plutonium power sources are decaying. Their instruments are shutting down one by one. Within a few more years, they'll go silent. But if 3I Atlas has been functioning for millions of years, it represents a level of engineering reliability we can barely conceive of. And studying it could teach us how to build things that last. Not just spacecraft everything. Infrastructure, power systems, computers, buildings. Think about what our civilization could accomplish if we could build things that functioned reliably for thousands of years instead of decades. We could plan on longer timescales. We could undertake projects that span generations. We could build for the future instead of just for ourselves. Third implication: someone solved the energy problem. Interstellar travel requires enormous amounts of energy. To accelerate even a small probe to a significant fraction of light speed requires energy equivalent to many nuclear weapons. And that's just for acceleration-deceleration requires the same amount again. And you need power for millions of years of operation. So if 3I Atlas is artificial, its builders had access to energy sources far beyond anything we currently use. Maybe fusion power, not the experimental reactors we're struggling to build, but mature, reliable fusion technology. Maybe antimatter. Maybe something we haven't even thought of. And here's the exciting part. The physics is the same everywhere in the universe. If they figured out how to harness fusion or antimatter or some other energy source, we can too. The laws of physics don't change. What's possible for them is possible for us. This is why studying potential alien technology isn't just about satisfying curiosity. It's about accelerating our own technological development. We could learn solutions to problems we're currently struggling with: energy, propulsion, materials science, artificial intelligence. Fourth implication: the light sail technology is real and practical. If Loeb is right that 3I Atlas used a light sail to slow down for capture, that's huge. Because we're developing light sail technology right now. The Planetary Society's Light Sail 2, launched in 2019, successfully demonstrated solar sailing in Earth orbit. The Breakthrough Starshot initiative is designing laser-pushed light sails that could reach Alpha Centauri in just 20 years. Japan's Icarus probe demonstrated interplanetary solar sailing in 2010. But all of these are experimental, proof-of-concept missions. We don't yet have operational light sail technology for interstellar missions. If 3I Atlas proves that light sails can survive millions of years of interstellar travel and function reliably for trajectory control, that's a game changer. It means light sails aren't just theoretically possible, they're practical. They work, and we should be investing heavily in developing them because they're the only propulsion technology we currently understand that could realistically enable interstellar exploration. Fifth implication, and this is the big one. We're not alone, and we're not first. If someone built 3I Atlas, they existed before us. They developed technology before us. They explored the galaxy before us. We're not the pioneers. We're the latecomers. That's humbling. For all of human history, we've assumed we're special, the pinnacle of evolution, the apex of intelligence. But if someone else achieved technological civilization millions of years before us, we're not special at all. We're just one more species that climbed out of the ocean, developed opposable thumbs, and figured out how to make tools. But here's the paradox. That's also empowering, because it means it can be done. Intelligence isn't a fluke. Technological civilization isn't impossible. Space exploration isn't a dead end. Someone else did it, which means we can too. And maybe, just maybe, they left breadcrumbs. Maybe 3I Atlas contains information, a primer on physics, instructions for building advanced technology, a map of the galaxy showing which stars have planets, which planets have life, which civilizations had developed technology. This isn't wild speculation. This is exactly what we put on the Voyager Golden Records information about Earth, about humanity, about our science and culture. We assumed that if someone found Voyager, they'd want to know about us. Why wouldn't they do the same? The question is, how do we access it? How do we decode it? How do we even know if it's there? And the only way to find out is to send a mission? Now let me tell you about what Avi Loeb is actually doing about all this, because it's not just talk. In July 2021, Loeb announced the Galileo Project, a systematic scientific search for evidence of extraterrestrial technological artifacts. The name is deliberate. Galileo was persecuted by the scientific establishment of his time for suggesting that Earth wasn't the center of the universe. He was right, and history vindicated him. Loeb sees himself in a similar position, proposing ideas that make the establishment uncomfortable, but being willing to collect the data that will settle the question empirically. The Galileo Project has three main objectives. Objective 1. Study unidentified aerial phenomena, UAP, commonly called UFOs, using high-quality scientific instruments, not relying on grainy videos from fighter pilots or eyewitness testimony, but deploying networks of telescopes, cameras, and sensors that can capture high-resolution data. Now, before you roll your eyes, understand that this is being done scientifically. The project has assembled a team of over 100 scientists from Harvard, Princeton, Cambridge, Caltech, and other prestigious institutions. They're building instrument arrays at multiple locations around the world. They're collecting data, and they're subjecting that data to rigorous analysis. Most UAP sightings will turn out to be mundane birds, balloons, aircraft, atmospheric phenomena. Loeb knows this. But if even one sighting turns out to be genuinely anomalous and can't be explained by conventional means, that's worth investigating. And the only way to know is to collect good data. The first Galileo Project telescope system was installed on the roof of the Harvard College Observatory in 2023. It consists of multiple cameras with different fields. a view and spectral ranges, an infrared sensor, a radio frequency detector, and a computer system that uses machine learning to identify and track unusual objects automatically. The data is being analyzed by graduate students and postdocs, and all findings are being published in peer-reviewed journals. This is not fringe science. This is mainstream methodology applied to a topic that has traditionally been ignored by mainstream science. Objective 2. Analyze interstellar objects like Oumuamua and 3I Atlas. This includes theoretical work on capture mechanics, observational campaigns to characterize the objects, and development of mission concepts to visit them. The Galileo project has already published several papers on 3I Atlas, including detailed orbital analysis, spectroscopic observations, and mission feasibility studies. They're building the scientific case for a dedicated mission and working to attract funding from private sources since government agencies have shown little interest. Loeb has been meeting with potential donors, billionaires interested in space exploration, foundations that fund high-risk research, even foreign governments looking to make a mark in space science. The goal is to raise $500 million to $1 billion to fund the Atlas Interceptor mission independently of NASA or ESA. Is this likely to succeed? Honestly, it's an uphill battle. Space missions are expensive and complex. But it's not impossible. The Breakthrough Starshot initiative has raised over $100 million from private donors. SpaceX has raised billions from private investment. If Loeb can generate enough public interest and scientific support, the funding could materialize. And that's where you come in. Your engagement with content like this, your discussions about 3I Atlas, your demands that this be taken seriously, all of that creates a cultural environment where funding such a mission becomes more plausible. Objective 3. Search for satellites or other technological artifacts that might be in orbit around Earth or other solar system bodies. This is the most speculative of the three objectives, but it's based on a serious question. If interstellar probes have been visiting our solar system for millions or billions of years, might some of them still be here? Think about it. If 3I Atlas is artificial and has been captured by our solar system's gravity, it's now in a stable orbit. It could remain in that orbit for millions of years. And if it's artificial, it's probably not the first probe to be captured. There could be dozens or hundreds of artificial objects in stable orbits around the Sun, around Jupiter, maybe even around Earth, just waiting to be discovered. Dr. James Benford, a physicist and engineer, published a paper in 2019 titled Lurkers, Co-Orbiters as SETI Observables, where he proposes that Earth's Lagrange points gravitationally, stable locations where an object can remain indefinitely with minimal energy expenditure, might be ideal parking spots for alien probes. These probes, which he calls lurkers, could have been watching Earth for millions of years, waiting for intelligent life to emerge. The Galileo project is conducting searches of Earth's Lagrange points using both ground-based telescopes and analysis of existing orbital data. They're looking for objects that don't match the characteristics of natural asteroids or human-made satellites. So far, nothing definitive has been found. But the search is ongoing, and as our survey capabilities improve, smaller and more distant objects become detectable. What I want you to understand is that Avi Loeb isn't just proposing wild theories and walking away. He's putting in the work. He's building instruments. He's collecting data. He's publishing papers. He's doing science. And whether he's right or wrong about 3I Atlas being artificial, the approach is the right one. When you have a hypothesis, you test it. You don't argue about it endlessly in theory. You go out and collect the empirical evidence that will settle the question. That's what science is supposed to be. And it's refreshing to see someone actually doing it, even when it makes him unpopular with his peers. Now we need to talk about something uncomfortable. Something that keeps me up at night, and should probably keep you up at night too. If 3I Atlas is an artificial probe, should we be trying to contact it? Should we be sending signals to it? Or should we be very, very quiet? This is the core dilemma of the dark forest hypothesis, and it's not just science fiction. Serious scientists, including Stephen Hawking before his death, have warned about the dangers of actively broadcasting our presence to the universe. Here's the logic. We don't know the intentions of other civilizations. We don't know if they're peaceful, curious, indifferent, or hostile. And in a universe where we don't know who else is out there, revealing your location is a potentially existential risk. Think about human history. When a technologically advanced civilization encounters a less advanced one, how does that usually go? The Europeans and Native Americans, the British and the Tasmanians, the Spanish and the Aztecs. It doesn't end well for the less advanced civilization. Ever. Now, some people argue that any civilization advanced enough to achieve interstellar travel must be peaceful and enlightened. They must have overcome their aggressive instincts, or they would have destroyed themselves before achieving space travel. But that's wishful thinking. There's no logical reason why technological advancement must be coupled with moral advancement. You can be very smart and very cruel. History provides plenty of examples. And even if most civilizations are peaceful, it only takes one aggressive one to make broadcasting your location a fatal mistake. In game theory terms, when the downside is extinction, even a small probability of encountering a hostile civilization makes silence the rational strategy. Stephen Hawking stated this explicitly in a 2010 interview. If aliens visit us, the outcome would be much as when Columbus landed in America, which didn't turn out well for the Native Americans. We only have to look at ourselves to see how intelligent life might develop into something we wouldn't want to meet. But here's the counter-argument, and it's compelling. We've already been broadcasting. For over a century, Earth has been leaking radio and television signals into space. Anyone with a sufficiently sensitive radio telescope within 100 light years could detect us. The cat's out of the bag. We're not hiding anymore, even if we wanted to. Moreover, any civilization capable of interstellar travel could probably detect Earth's biosignatures, oxygen in our atmosphere, chlorophyll in our vegetation, without us saying a word. A sufficiently advanced telescope could analyze Earth's spectrum from dozens of light years away and conclude that life exists here. So maybe the question isn't whether to reveal ourselves, but how to present ourselves. And if 3i Atlas is a probe, this question becomes immediate and urgent. Avi Loeb has proposed a fascinating idea. What if we intentionally activate 3i Atlas? What if we send a spacecraft to it and deliberately signal it using radio waves, lasers, or even physical interaction? If it's a probe, it might be designed to respond to such signals. It might contain a message or instructions that unlock when contacted by an intelligent species. But the risks are real. What if activating the probe triggers a beacon that broadcasts Earth's location to whoever sent it? What if it summons a response that we're not prepared for? What if it's not a scientific probe, but a weapon, lying dormant for millions of years, waiting to be triggered? These sound like science fiction scenarios, but they're based on reasonable extrapolations. If you're going to send probes across the galaxy, you might want them to include defense mechanisms or data protection protocols. You wouldn't want just anyone accessing the information they carry. Dr. Stuart Armstrong at the Future of Humanity Institute has written about the assassin probe scenario. What if a hostile civilization sends probes throughout the galaxy programmed to lie dormant until they detect technological civilizations, then report back or directly attack? From a strategic perspective, this makes sense. You can't police the entire galaxy, but you can seed it with probes that act as your eyes and ears or your weapons. Now, do I think 3i Atlas is an assassin probe? No, probably not. The probability is low, but it's not zero. And when the stakes are existential, even low probability risks demand serious consideration. So what should we do? This is a question for all of humanity. not just scientists or governments. This is a decision that affects everyone on Earth, and we should make it democratically, with full knowledge of the risks and potential benefits. Here's what I think. We should send a mission to study 3I Atlas. We should examine it closely, analyze its structure and composition, look for any signs of technology or artificial construction. But we should be cautious about actively signaling it or attempting to activate it until we understand what we're dealing with. Think of it like encountering an unexploded bomb from an ancient war. You want to study it, understand it, maybe even defuse it and learn from its technology. But you don't want to hit it with a hammer to see what happens. And here's the crucial point. We need international cooperation on this. If one country or organization decides to signal 3I Atlas on their own, they're making a choice that affects everyone. This can't be a unilateral decision. The United Nations Outer Space Treaty of 1967 needs to be updated to address scenarios like this. We need protocols for how to handle potential extraterrestrial artifacts. We need agreed-upon procedures for who decides whether to attempt contact and under what circumstances. Because right now, we have no such protocols. Anyone with a powerful enough transmitter could send a message to 3I Atlas. Elon Musk could do it. China could do it. A well-funded private individual could do it. And the rest of us would just have to live with the consequences. This isn't acceptable. This is too important to be left to chance or individual decision-making. We need global governance mechanisms for this scenario. And we need them before the Atlas Interceptor mission launches. Because once we're there, in close proximity to 3I Atlas, the temptation to make contact will be enormous. And whoever is controlling that spacecraft will have the power to make a decision that affects all of humanity. Are you okay with that? Are you comfortable with that power being concentrated in the hands of whoever funds and controls the mission? Or do you think this requires broader input, broader consensus, broader responsibility? This is not a rhetorical question. This is something you need to think about, because it's going to happen. Maybe not this year, maybe not next year, but within the decade, we will have spacecraft capable of rendezvousing with 3I Atlas. And at that point, the question of what to do becomes immediate and unavoidable. What's your answer? Drop it in the comments. Because this conversation needs to happen now, before we're forced to make decisions under pressure. Let's get practical. If we decided tomorrow to send a mission to 3I Atlas, how long would it take? What are the technical constraints? When could we realistically have answers? First, we need to understand 3I Atlas's orbit. Based on current observations, the object is in an elliptical orbit around the Sun, with a semi-major axis of approximately 27 astronomical units. That's 27 times the distance from Earth to the Sun, or about 4 billion kilometers. Its orbital period is approximately 140 years, meaning it takes 140 years to complete one orbit around the Sun. Right now, in late 2024, 3I Atlas is approximately 18 astronomical units from the Sun, in the outer solar system between the orbits of Uranus and Neptune. It's moving outward, heading toward its aphelion, the farthest point from the Sun, which it will reach around 2060. For our mission to intercept 3I Atlas, we need to minimize travel time and fuel requirements. This means launching when Earth is positioned favorably relative to the object's orbit and using gravity assists from planets to increase velocity. Dr. Damon Landau at NASA's Jet Propulsion Laboratory has done preliminary trajectory analyses for an Atlas Interceptor mission. His findings, presented at the 2024 International Astronautical Congress, show that the optimal launch window is 2027 to 2028. During this window, Earth, Jupiter, and 3I Atlas are positioned such that a spacecraft could use a Jupiter gravity assist to reach the object in approximately 12 years, arriving around 2039-2040. This is similar to the trajectory used by New Horizons to reach Pluto, which took 9.5 years. The spacecraft would need to be fast averaging about 20 kilometers per second relative to the Sun, but this is within our current capabilities. The Delta IV Heavy rocket or SpaceX's Falcon Heavy could provide sufficient launch energy, with an upper stage for additional acceleration after Earth escape. Total mission cost, including spacecraft development, launch, and 15 years of operations, approximately $500 million to $800 million, depending on payload complexity. For context, that's less than half the cost of the New Horizons mission to Pluto, $780 million, and a tiny fraction of the James Webb Space Telescope, $10 billion. So it's affordable. It's technically feasible. The launch window is approaching. Why isn't this happening? Politics and priorities. NASA's budget is largely committed to established programs. Artemis lunar missions, Mars sample return, maintaining the International Space Station, and operating existing spacecraft like James Webb. There's little flexibility for new, unplanned missions. ESA faces similar constraints, with commitments to the Jupiter Icy Moons Explorer, JUICE, and other flagship missions consuming most of their budget. Getting a new mission approved requires years of planning, committee reviews, scientific justification, and political approval. The process typically takes 10 to 15 years from initial proposal to launch. We don't have that time if we want to hit the 2027 to 2028 window. The only realistic path is private funding. A billionaire or consortium of donors who can move quickly, hire the engineering team, contract with SpaceX or another launch provider, and get a spacecraft built in 3 to 4 years. This has happened before. Yuri Milner funded Breakthrough Starshot with $100 million of private money. Dennis Tito funded a Mars sample return concept study. The Planetary Society crowdfunded the LightSail missions. Private space missions are possible, but they require someone willing to write a very large check for something with no commercial return. This is pure scientific exploration and curiosity-driven research. The only return is knowledge. And in our current economic system, that's a hard sell. This is where public pressure matters. If there's enough public interest, enough media attention, enough people demanding that this mission happen, it becomes easier to attract funding. Space missions are prestige projects. Donors want recognition. If supporting the Atlas Interceptor makes someone a hero of scientific exploration, they're more likely to fund it. So talk about this. Share this video. Write articles. Make podcasts. Generate buzz. Make 3i Atlas a cultural touchstone. Make it something that people care about, something that matters. Because the clock is ticking. The 2027 to 2028 launch window is optimal. Miss it, and the next good opportunity isn't until the mid-2030s. That's another decade of waiting. Another decade of 3i Atlas drifting through our solar system, carrying whatever secrets it holds, unexamined. And here's the thing that really frustrates me. We have everything we need to do this mission, except the will. The technology exists. The rockets exist. The scientists exist. The trajectory is calculated. We just need someone to decide it's worth doing. And that decision should be obvious. When was the last time we had an opportunity like this? An interstellar object captured in our solar system, available for study? Never. This has never happened before. And it might not happen again for millions of years. This is a once-in-a-civilization opportunity. And we're on the verge of letting it slip away because we can't get our act together to fund a mission that costs less than a single luxury yacht. That's insane. Future generations will look back at this moment and ask, what were they thinking? How could they not prioritize this? How could they let this opportunity pass? And we won't have a good answer. We'll just have excuses. Bureaucratic inertia, budget constraints, lack of consensus. All the usual reasons why humanity fails to do great things even when the path is clear. Don't let that happen. Be part of the generation that demanded better. that insisted we investigate three-eyed lists, that refused to let this moment pass. Now let's zoom out. Let's talk about what all of this means for how we understand ourselves, our civilization, and our place in the universe. Because this isn't just about a space rock, or even about alien technology. This is about who we are and what we're becoming. For most of human history, we believed Earth was the center of everything. The sun, the moon, the stars, they all revolved around us. This made sense from our perspective. We could see the sun moving across the sky. We could watch the stars wheel overhead. And it felt true that we were the focal point, the reason for it all. Then Copernicus, Galileo, and others showed that we're not at the center. Earth orbits the sun. We're just one planet among several. This was psychologically devastating for many people. It challenged religious doctrines. It diminished humanity's special status, but we adapted. We created a new narrative. Maybe we're not at the center geographically, but we're still special. Earth is the only planet with life. We're unique. We're alone in the universe, which makes us precious. Then we discovered that stars are other suns, that galaxies are vast collections of stars, that the universe contains billions of galaxies. And we realized that Earth is one planet around one star in one galaxy among billions. We're not special in location. We're not rare in cosmic terms. We're a tiny speck in an almost incomprehensibly vast universe. So we adjusted our narrative again. Maybe we're common in cosmic terms, but we're still alone. We haven't found anyone else. The universe might be vast, but we're the only intelligence, the only consciousness, the only life that can contemplate itself and the cosmos. That makes us special in a different way. And that narrative has held for the past few decades. We search for signals from space and find none. We look at nearby planets and find no evidence of life. We catalog exoplanets and find none that are exactly like Earth. So we remain alone as far as we can tell. But what if 3-Eye Atlas changes that? What if it's evidence that we're not alone after all? What happens to our narrative then? Here's what I think. It would be the most profound shift in human self-understanding since Darwin proposed that we evolved from earlier life forms. Because it would mean we're not special at all. Not in location, not in rarity, not in uniqueness. We're just one instance of a phenomenal intelligence that occurs throughout the universe. Think about what that does to every human institution and belief system. Religions that claim humans are the pinnacle of God's creation would need to radically reinterpret their teachings. Philosophies based on human exceptionalism would need to be revised. Political systems that assume humans are the ultimate stakeholders would need to expand their moral circle. It would force us to grow up as a species, to recognize that we're not children in a playground built just for us, but one species among potentially millions, sharing a galaxy that doesn't care about our petty squabbles and tribal conflicts. And here's what excites me about that. It might be exactly what we need, because right now, humanity is stuck. We're fighting over resources, borders, ideologies. We're damaging our biosphere. We're risking our future for short-term gains. We're acting like children who think the world exists just for them. But if we really knew that we're not alone, that might change our perspective. It might make our conflicts seem small and pointless. It might inspire us to get our act together, to become a civilization worthy of joining a galactic community. This is called the overview effect in psychology. When astronauts look at Earth from space and see it as a single, fragile sphere with no visible borders, they report a profound shift in perspective. National conflicts seem absurd. Political divisions seem arbitrary. The only thing that matters is protecting this one small world and the life it contains. Confirming that we're not alone could trigger a species-wide overview effect. It could be the catalyst that finally unites humanity around common goals: survival, exploration, growth, and contribution to something larger than ourselves. Or, and I need to be honest about this, it could go the other way. It could trigger fear, xenophobia, and tribalism. Some people respond to feeling small and insignificant by doubling down on their beliefs, becoming more defensive, more aggressive, more determined to assert their importance. We've seen this pattern throughout history. When European explorers encountered other civilizations, some people responded with curiosity and openness. Others responded with conquest and domination. When new scientific discoveries challenge existing beliefs, some people embrace the new knowledge. Others reject it and cling more tightly to comfortable falsehoods. So the question is, which kind of species do we want to be? When faced with evidence that we're not alone, do we respond with curiosity or fear? With openness or defensiveness? With growth or regression? And here's the thing, we get to choose. This isn't predetermined. The future isn't fixed. How humanity responds to the discovery of extraterrestrial intelligence, if that's what 3i Atlas represents, depends on the choices we make now, today, and how we think about these questions and talk about them with others. If we approach this topic with fear and suspicion, that's what will dominate the cultural conversation. But if we approach it with wonder, curiosity, and excitement, if we frame it as an opportunity rather than a threat, it can shape the collective response. So I'm asking you to be thoughtful about how you engage with this topic. When you discuss 3i Atlas with friends, family, or online, emphasize the positive possibilities. The knowledge we could gain, the technologies we could learn, the perspective we could achieve, the inspiration it could provide for solving our problems here on Earth. Because narratives matter. Stories matter. The stories we tell ourselves about who we are and what we're capable of shape what we actually become. And right now, we have the opportunity to write a new story for humanity. A story where we're not alone in the universe, where we're part of something larger, where our problems, while real and important, are not insurmountable, where we have examples to learn from, neighbors to meet, and a future to build that's bigger and stranger and more wonderful than we ever imagined. That's the story I want to be part of. What about you? So where do we go from here? What are the concrete next steps? What can you, personally, do to help make the Atlas Interceptor mission a reality? First, stay informed. Follow the ongoing observations of 3i Atlas. Scientists are continuing to refine its orbital parameters, analyze its light curves, and collect spectroscopic data. Every few months, new papers are published with updated findings. The more we learn, the stronger the case becomes for a dedicated mission. The Galileo project maintains a website with regular updates. Avi Loeb publishes articles in Scientific American and posts updates on social media. NASA's Jet Propulsion Laboratory tracks all known interstellar objects. Stay connected to these sources. Second, support the science. If you're in a position to donate the scientific research, consider supporting organizations that are working on this. The Galileo project accepts donations. SETI institutes around the world need funding. University research programs that study interstellar objects need support. Even small donations matter. They signal public interest. They provide seed funding for preliminary studies that can lead to larger grants. They show scientists that people care about this work, which encourages them to pursue it even when it's not fashionable or well funded by traditional sources. Third, advocate for this mission. Write to your representatives in government. Express support for funding exploration of interstellar objects. Space agencies listen to public opinion. When the Hubble Space Telescope was in danger of being abandoned, public outcry saved it. When the Pluto flyby mission was on the chopping block, grassroots support kept it alive. Your voice matters. Use it. Tell your elected officials that you want humanity to investigate 3i Atlas. Tell them it's a priority. Tell them that future generations will judge us by whether we seize this opportunity or let it pass. Fourth, spread awareness. Share this video. Talk about 3i Atlas with people you know. Write blog posts. Make TikTok videos. Create art inspired by it. Get creative. Make it part of the cultural conversation. The more people know about 3i Atlas, the more pressure there is to take it seriously. Science doesn't happen in a vacuum. It happens in a cultural context. And when something captures the public imagination, resources flow toward it. Think about how much money has been invested in Mars exploration, because Mars fascinates people. Think about how the James Webb Space Telescope became a cultural phenomenon when its first images were released. That's the power of public engagement. That's what we need for 3i Atlas.